In our last video, we saw that hot hydrogen atoms emit light at discrete frequencies rather than the continuous spectrum that's characteristic of blackbody radiation. And we saw that the characteristic frequencies in the hydrogen spectrum fit a striking pattern, which is described by the Rydberg equation, that 1 over the wavelength is a constant times the difference between the reciprocals of two squares. And this pattern was very exact. It fit the observations very well, but there wasn't any theory to explain where it comes from until a Danish physicist named Niels Bohr came along. And Bohr was an interesting guy. He didn't believe in photons. He didn't believe that light carried discrete packets of energy, but he also thought that Max Planck, Albert Einstein, and the other physicists who were dabbling in this idea of quantization, he thought that they were onto something. And Bohr's thinking was based on the idea of something called angular momentum. So he believed that the electron in a hydrogen atom travels in a circular orbit around the nucleus, and because it's moving in a circle, it has some angular momentum. Just like linear momentum describes the tendency of an object to move in a straight line, angular momentum describes the tendency of an object to move in a circle. And so anything that travels in an orbit has some angular momentum. And Bohr's key idea was that the minimum angular momentum that an electron could have in hydrogen was related to the Planck constant h, and specifically thought that it was h divided by 2 pi. The 2 pi shows up a lot when we were talking about circles. And furthermore, Bohr believed that the electron could also, that there were other circular orbits that were possible, but that they all had angular momentum with that was a multiple of this h over 2 pi. So the smallest orbit would have an angular momentum of h over 2 pi. The next orbit would be twice that, and then 3 times that, 4 times that, and so on. And if you calculate the radius of the orbit using this angular momentum, what you come up with is that the radius of the orbit of an electron in hydrogen is equal to some number squared times a constant a0. And the constant here, n, is called the principal quantum number. And it's just an integer, 1, 2, 3, 4, and so forth. And then this a naught is the so-called Bohr radius, and it's equal to about 53 picometers. So the first orbit, the first possible orbit that an electron could have in hydrogen, according to Bohr, had a radius of 1 squared times a naught, so 53 picometers. That would be for the n equals 1 orbit. And then when n equals 2, the radius would be 2 squared, or 4 times the Bohr radius. And so it would be the radius would be 4 times as large for the second possible orbit. And then the third possible orbit would be 3 squared, or 9 times as large as the first one. The fourth one would be 16 times as large as the first one, and so on. And so the orbits get larger with the square of this principal quantum number. Now, before we continue, I want to give you guys a sense of scale. If you think about the first orbit in the hydrogen atom, where the radius is the Bohr radius of 53 picometers, I want to give you a sense of how big that is compared to the nucleus. So if the entire hydrogen atom were blown up to be the size of a hot air balloon, the proton in the nucleus of the hydrogen would be the size of a grain of salt. So the nucleus is unimaginably tiny, even within an already tiny atom. And so really, almost all of the space in an atom is taken up by the electrons. The nucleus is just a pinprick of mass and charge at the center of the atom. So anyhow, returning to the story, once you know the size of the electron orbit, in a hydrogen atom. You can calculate its energy, and this is based on the potential energy between charged particles. If you have two charges that don't interact, such as a proton and a neutron, if they don't interact at all, their electrostatic energy is zero. If you have two like charges, such as two protons, they repel each other, and that corresponds to a positive potential energy. And if you have two particles with opposite charge, like a proton and an electron, then they attract one another, and the potential energy is negative. And that's the situation in a hydrogen atom. So if you calculate the potential energy of an electron at particular distances from the nucleus of a hydrogen atom, the potential energy is very low when the electron is close to the nucleus, and then it goes up and sort of flattens out as the electron gets further and further away. And if the electron, as the electron becomes infinitely far away, the energy gets closer and closer to zero. So if you take this energy curve and you map onto that the distance of the different orbits in the Bohr model, the first orbit at a distance of 53 picometers has a low energy, and that's the energy for the first orbit. The second orbit is 4 times as far from the nucleus, and its energy is 1/4 as deep as the first one. Likewise, the third orbit is 9 times as far from the center, and its energy is 1/9 as deep as the first orbit. The fourth orbit would have an energy that's 1/16 as deep as the first one. And so you have this pattern where these so-called energy levels in hydrogen get closer and closer as you go up in this principal quantum number n. So if I focus on these energy levels and sort of rearrange the picture here, you've got this kind of ladder of energies in the hydrogen atom, and when you calculate the energy of the nth orbit ends up being, it's negative, and it's negative a constant k divided by n squared. This k is an amount of energy. It's 2.179 times 10 to the minus 18 joules. 10 to the minus 18 joules is an attojoule. So for the first orbit, when n equals 1, the energy would be this k divided by 1 squared, so that corresponds to negative 2.179 attojoules of energy. The second orbit is 1/4 as deep as that when n equals 2, and that's negative 0.545 attojoules. The third orbit is 1/9 as deep as the original, so negative 0.242 attojoules. The fourth one is 1/16 as deep as the first, so that's negative 0.136, and so forth. And you can keep drawing in these energy levels. Here's the one for n equals 5, n equals 6, and they do get closer and closer together as you go up in the value of n. And so this is the energy picture that you come up with in the Bohr model. And another key idea that Niels Bohr had was that a hydrogen atom can change energy, so the electron can move from one orbit to another. And one way that this can happen involves light. So for instance, if an electron in the third orbit with n equals 3 were to drop down to the second orbit with n equals 2, one way that can happen is if the atom emits a photon of light. And the energy that would be carried off by that photon is just equal to the change in the energy of the atom. So when the electron goes from n equals 3 to n equals 2, it's losing energy. That lost energy is carried off by the photon. And the amount of that energy is simply the difference between the two energy levels in the hydrogen atom. So the difference between the energy of the upper level minus the energy of the lower level. And it turns out that this transition from the third orbit to the second orbit, the energy of that transition happens to perfectly match the red line in the hydrogen spectrum. And similarly, a transition from the fourth orbit to the second orbit matches the energy of the cyan photon in the hydrogen spectrum. Transition from n equals 5 to n equals 2 produces the blue photons in the spectrum, and a transition from 6 to 2 produces the violet photons in the spectrum. And the transitions don't have to stop at n equals 2. You can have transitions from a high orbit down all the way down to n equals 1. The thing is, those transitions involve a much larger amount of energy, and they would correspond to photons in the ultraviolet part of the spectrum. And so there would be one wavelength that would correspond to a transition from 2 to 1. Another wavelength would correspond to a transition from 3 to 1, and so forth. And those photons would all be ultraviolet. Similarly, transitions down to the third orbit have much less energy, and they correspond to photons in the infrared part of the spectrum. So the Bohr model works really well in describing the spectrum, the observed spectrum for the hydrogen atom. It fits not only the visible lines in the spectrum, but it also perfectly fits the lines in the ultraviolet part and the infrared part. And moreover, this model works for any atom that only has one electron. So, it certainly works for hydrogen. Hydrogen has one proton in the nucleus and one electron outside the nucleus. And if you look at atoms with more charge in the nucleus, the charge of the nucleus, the number of protons, is the atomic number Z. And in general, if you have an atom with an atomic number of Z, the model is the same, but because the charge of the nucleus is greater, that tends to pull the electrons in closer to the center, and so the radius of the atom becomes, instead of just n squared times the Bohr radius a naught, it's n squared divided by z times the radius a naught. And similarly, with the greater charge in the nucleus, that also makes the forces in the atom stronger, and so the potential energy is a bigger number, and so the energy levels are deeper down, and the energies are negative k times z squared divided by n squared. And so what this means is that for the hydrogen plus 1 ion, the helium plus 1 ion, the charge of the nucleus is the atomic number z is 2, and so the size of the electron orbit in a helium plus 1 ion would be half as big as in a hydrogen atom. So this is the first and second possible orbits in the helium plus 1 ion. And then the energy levels are going to, they follow the same pattern as in the hydrogen atom. It's just that they're 4 times deeper because of that greater attraction between the nucleus and the electron. Similarly, in a lithium 2 plus ion, again, there's just one electron, but now the charge of the nucleus, Z, is 3. So the orbits, the possible orbits around the nucleus are 1/3 the size of the ones in hydrogen, and the energy levels are 3 times as deep. So, atoms like this that have just a single electron are called hydrogen-like atoms because there's just one electron, and that's the situation that you have in hydrogen. Now, so the Bohr model works brilliantly in describing atoms that have a single electron. It breaks down, though, as soon as you try to describe an atom with more than one electron. So helium, for instance, a neutral helium atom has 2 electrons, and if we imagine those electrons in circular orbits a la the Bohr model, the energies that you predict from that do not match the spectrum for hot helium atoms at all. The model completely breaks down. And to see why, think about the solar system. So in some ways, the solar system is very similar to what you might imagine a multiple electron atom as looking like. We've got bodies moving in orbits around the center. But the thing is, in the solar system, the planets have very little mass compared to the sun at the center. And so, although all the planets are attracted to the sun, they only exert tiny forces on each other. So the forces between, say, Venus and Earth are very small. And so the forces that dominate the solar system are all the attractions between the planets and the sun. Now, in an atom like helium, you also have attractive forces that attract the electrons to the nucleus, but even though electrons have very little mass, the charge of an electron is the same magnitude as the charge of a proton. And so the forces between electrons are very strong. They're comparable in strength to the attractive force between the electron and the nucleus. And moreover, since electrons all have the same negative charge, they repel each other. And so the situation in an atom with more than one electron is much more complicated than in something like the solar system. And so it's really no surprise that the Bohr model breaks. But it turns out that there were bigger problems with the Bohr model. And this is something that we're going to be looking at in the next video. But one thing that I really want to emphasize is that as we're going to see, it turns out that Niels Bohr was wrong about the idea that electrons move around the nucleus in circular orbits. But there were a lot of things about his model that he got right. So he was right that atoms have discrete energy levels, and that electrons in atoms, they do have more energy when they're further from the nucleus. He was also right that the discrete lines in the spectrum of a hot atom arise from these quantized atomic energies. So he was right about a lot of things, and it's remarkable that although the Bohr model is based on an incorrect idea, the mathematical model that came out of that idea worked perfectly for hydrogen atoms. And really to get a better picture of the atom really required some radical new ideas, and that's what we're going to look at in the next video.